That's what we do in breadth first, right? Let's do this question by breadth first. Have V1 then let's do this. We use BFS up to this question. Firstly, we need then we write things down. But then in this only we do the BFS tree as well. How we consider the BFS tree. We start with the, let's say you're starting with the B7 vertex. Let's start with this one this time. Start with B7 vertex. From there, the two vertices V3 and V2. So you write them down. V3, V2. Then after this, you start with V3. So you're done exploring this one. So V7 is done. You can write V7 here. Then next is V3. So you start with V3. V3 and V3 is connected directly connected to V5 and V1. So you write down V5 and V1. And with this, we're done with V3 too. So we write the V3 next. And then we have V2. So for V2, we have V4, V5, and V7, and V1 too. But V1 is already done. So we have V4, V5,
Good evening,
V7.
ma'am.
Good evening. This, and with this, we're done with V2. Then we have V5 in the list. So V5 has V3 and V2 and V6. But V2, V3 are already done. So just V6 is there. Write down V6. And then with this, V5 is also done. V5 is done. Then coming to V1, you have V2, V3. But I think they're already done. So V1 is also explored. Then V4. V4 has V6, which is already, I think we have all the vertices there, right? From V1 to V7. That means every vertex has been explored. So you can just write them down in this order only. V4, then V5, then V7, and then V6. Because every vertex has been explored. This will be your order when you will be doing things starting from here using the BFS approach. This is it. And then there's one thing called a tree. So how do we make the BFS tree? It's just starting with V7. So V7 comes first on level 0. This is your level 0. Then after V7, you have V2 and V3 on first level, directly connected to V7, right? So V2, V3 next on level 1. Then V2 has V1, V5, V4, and V7. But you started with V7 only. So we've repeated V7 here. You should not have V7 here. Came from V2, right? Where did it come from? Yeah, we should not have this V7 thing, yeah, because it was that was the vertex that we started with. We don't need V7 here. So while making the BFS tree, you have V1. Then sorry, we're starting with V7. So you have V7, then V2, V3 on the first level. Then on second, your level 2 is this. Those that are directly connected to V2 and V3 will be on level 2. So V2 is directly connected to V1, but it's all V1 here. then V5 and V4 and V5. V4, V1, V4, V5, and V7 is already there, but it's written it here, right? And then with V3, you have V5. V5 is already mentioned there, so you don't have to mention it here. Then V1 is already mentioned, so you don't need to mention it again, and that's it. So with V3, you have nothing. And then continuing this was your level 2. This is level 2. And then with V1, you have V2 and V3. They've already been covered. Then with V5 and V4, you have V6. So you can write it down under one of these. But make sure you're only writing it down under one of these because it's a tree and it's supposed to have no sightings here. It's not supposed to have sightings. So make sure that you're not writing, if you write V6 under both of these, then it will create a sighting here. This is the sighting. Not be
Ma'am,
including any edge that forms a sighting. This will be
we
a
can,
level 3.
ma'am, just a doubt.
Yeah.
We can put V5 under V3.
Yeah, you can do that, but since we mentioned V2 first here, so if you start with V3, if you do it this way, V7, and then you mention V3 first here, V2, it depends on how you're doing things here. Like in this one, they've mentioned V3 first. So as per this search, and BFS search is actually not unique. Like we did V3 first here, and then V2 later, right? But we could have used V2 first, V2 here, and V3 here.
Okay.
The order that you're going to get, this is not going to be unique, right?
Yes. Okay, got it.
So you can change this thing here. If you do this here, then you'll have V5 under this. You'll do it this way. V3 is directly connected to V5 and V7 and V1. So V5, V7 and V1 will come under V3 and V4 will come under V2.
Ma'am,
And then you
V7
can,
on top.
Ma'am, V7 is already
V7 is
there.
on top.
oh yeah,
V7.
I keep forgetting. Thank you. Yes. Here, we started with this only. So you'll have only these two things here. Then you'll have this and then V6 is left, which is under V5, so you can write it this way. This is also a BFSP for the same graph with different levels. Now,
Okay, ma'am, got it.
BFS tree actually helps you. One of other applications of BFS tree is it helps you identify the shortest route, right? Like if you're starting from here V7, so you can identify the shortest route to V4, which you can't from here. It's a little messed up in here. This one is sorted. You know that this, and how do we identify the shortest path? So this is level 0, level 1, this is level 2. So the shortest path then is 2. So everything that's on level 2 has shortest paths. So the shortest path, shortest path it's called, is of length 2. Length of the path is actually this. If you have V1, V2, and V3, then the length here is 2. So that's the length of path. So here, that length of path gives you the shortest path. So this, for V1, your shortest path will be 2. You can directly see it from here, provided you're starting your search from V7. The shortest path between V7 and V1 in this case will be 2. Is that okay?
I mean,
That's one of the applications of BFS tree. Yes.
I mean, the right what we have written V1, V2, V3, what's that?
This is a path. We were discussing the length of path.
But V1 is not connected to V2 now. I'm here.
No,
V1,
this
V2.
is Just
Okay.
a
Okay.
random example. Random example. Not from there. Okay. So this is one example, and then we've covered the BFS tree. We've covered the algorithm. This one using the queue, and yeah. So let's do this thing then. BFS tree, and which can be a possible branch in a possible branch, which can be an edge in the original graph. So some questions are given or phrased like this. So you'll be given a BFS tree uh, like this. Let's say you have this tree.
Ma'am,
Yes.
I have a question regarding that. All the vertices on one level, that is level 1, maybe level 2, does it depend on the choice in a very, suppose there is a very complex and large graph, and we are making choices about the there are various options. Suppose I can go here, I can go to V2 or V3 or V4. Suppose I am choosing V3, maybe V4. So does does number of vertices on a level depend upon these choices, or by any path I will get the same set
No,
of vertices on one level?
I got your question. Uh, the number of vertices, in fact, these vertices will remain on level 2 only. So whichever approach, whichever vertex you choose first, it doesn't matter. What we're doing here is we're exploring the breadth first, right? So the level, you have these levels, and these vertices V5, V1, V4 will always be on level 2 only. So no matter what path you choose V2 first, V3 first, because this is about the shortest path. What you do here is first you write down all the vertices directly connected to V7. Then you write down all the vertices directly connected to V3 and V2, right? So if V5 was connected to something else too, let's say V5 is connected to some some vertex on this level 6, then V5 will come here only because it has been explored, it has been visited first via this route, right? So you wouldn't be writing it on level 6. It will come here only.
Got
So the
it.
vertices on this level are not going to change, no matter which route you choose.
Got it.
So let's say a BFS tree. Then now this is a tree corresponding to some graph, right? There'll be a graph in the sense like this is the graph, and then this is the tree, right? So let's say this is, you have been given the BFS tree, and now you have been asked about the graph. Graph, you won't be asked exactly the graph how it looks, but you can be asked if this could be a possible edge, if CD could be an edge in the original graph. That is something you can be asked, right? So coming to CD, can CD be an edge in the original graph? How do we proceed with the BFS tree construction? We first write A, and then we write everything connected to A. Now, can CD be an edge here? In the original graph, can CD be an edge?
No, madam.
No, ma'am.
Why?
Because CD does
It
not
should
have
come under
any,
below that. If it is
there is no
the edge,
connection.
yeah, it should come under C, right? If D is the edge of C.
It cannot be a direct edge, but through via A, we can have like a connection we can have.
No, connection we're not talking about. We're talking about edges, a direct edge. Can we have CD as an edge in the original graph?
No, there is no edge between C and D.
There, here, there's no edge. Have a
Yeah,
look at this graph. If you look at this graph, V2 and V7, V2, V7, V3,
V2 and V7 have an edge.
yeah, V2 and
right, they have
V7
an edge.
clearly have
That's
edge.
okay. I'm looking for V6.
We can say that V1 and V4
Okay,
don't have a
V6
direct.
and V4 have an edge, right? There we have there is an edge between V and V6, but we don't have an edge here from V4 to V6.
Yes, ma'am.
Right.
So there could be edges here in the original graph that are not present in your tree, right? So if I give you this tree and then I ask you, can there be an edge between B4 and B6? Then the answer is yes, right? Because you can obviously see it from here that there is an edge between B4 and B6 in the original graph. That's my question here. I know that there is no edge between C and D here, but can there be an edge between C and D in the graph?
We can have.
No, ma'am.
Why can we have an edge between C and D?
No, we can't. But same level, we don't have that, right?
Yeah, ma'am. For the same level, we cannot have it.
For the same level, you can't. Okay. When you construct a graph, this is, you start with A, then you write down all the vertices that are directly connected to it, right? And then let's say if C and D, if this is the graph, let's say, if this is your original graph, then how do you draw the BHS tree? You start from, give a search from here, obviously A, you write down A, then you write down all of those that are directly connected to it. Then what do? You start with B, right? And then you write down all the ones that are direct, that have an edge with B. Then the C ones, then the D ones. Then why can't you have an edge here? This edge has already been, this
So there is
D has already been discovered. Why we're not, if this was a graph, then this will be its BFS tree, right? Because you start your search from A, and
Ma'am,
you
to
write
make a
down B,
graph
C, D.
from a tree, if you are making graph,
We're
if
not making a graph.
no,
We're
ma'am,
just,
ma'am, if we are making a tree from a graph, so do we have to take the upper A only, or we can take B, C, or D also?
depends on where your graph start, where your search starts from. BFS is a search, right? So you
Okay,
start your search from the vertex that you start your search from. That's what you write here on the top.
we can also start from B, na, ma'am.
You can start, but you have already been given this tree, right?
Okay, ma'am. Okay.
Okay.
and
So
then
if you,
how can we be sure about that CD have edge or not?
we're not sure about it. The question is, that's why it asks, can this be an edge? Can this be an edge? We're not saying that this is an edge in the original graph. We're saying, can this be an edge? Is there a possibility that this is an edge there? That's it.
Ma'am, what was
Yeah.
the answer? Is the age possible?
Yeah, it is possible. No, we've just shown it. If this is your graph, try making the graphs. Everyone just take 1 minute and try to make the BFS tree for this one. And test if you get this thing or not.
Ma'am,
Okay.
in this sense, we can also say that BC can have an edge.
Yeah, they can also have an edge. And in general, every vertex, all the vertices on the same level can have edges.
Ma'am, on the
Okay,
same
got
level, that means A and F cannot have an edge, right?
A and A, yeah, A and A is never an edge, right? We've
No,
never
no,
studied
ma'am.
something.
I was speaking about
So
A and F.
A and F, okay. We'll come to
Yes.
different levels later. I just wanted to
Oh,
make clear that everything that's on the same level, every vertex on the same level, they can have edges between them.
oh, okay, okay.
Ma'am,
Understood.
ma'am, can
Thank you.
even F and G have?
What?
Even F and G has an edge.
F and G. Yeah, F and J can also have an edge. These two can have an edge. But because what happens if F and G will have an edge, if you'll make the graph, what happens here is you're on B, C, D level. Then you write down, you start with B and you write down all the vertices that are directly connected to B. That is E, F, right? G is not directly connected to B, right? So you write E
Yes,
and
ma'am.
F, then you come to C, the next vertex. Then exploring B, come to C. Then on C, directly connected ones are G and H. So you write down G and H. Then next up you write, so this edge is not creating a problem, right?
Yes, ma'am.
Because even if we have an edge here, in the tree, we won't make this edge here, right?
Yes, ma'am.
And even if we don't have it, then also we're going to have the same graph. So on the same levels, you can have edges there. Then coming to different ones, let's say we're talking about A and H. Yeah, yeah. Let's take A and H. So we're taking A, yeah, or A or G, someone suggested. So let's say A and G. So if we're talking about A and G, can A and G have an edge?
No, ma'am.
No, ma'am.
So the answer is no. Why is it no? Because if you have an edge from A to G, if you have an edge here, then this G would have been here, right? On this level. You start with A and then you write down every vertex that has a direct edge, that has a direct edge with A, right? So if G had a direct edge with A, G would be here, not here. G would be on the first level, but you've written it on the second level. That means G, this cannot be an edge. That means in the original graph, there's no way this can be an edge. Is that okay?
Yes, ma'am.
And then let's say, so this was about this one. Let's take B and G this time. Can B and G have an edge? B to G.
Yes.
This is BG.
Yeah.
Yes, ma'am.
Okay, so the answer for this one is no. And no, why no? Because when you start the fundamentals of BFS, making a BFS tree, is you start write the starting vertex here. Then you write all the vertices directly connected to it. And then you start with the first one. So if you have written it like this, B, C, D, then you start exploring B. And when you are done exploring B, then you come to C, right? And if you've written it in this way, C, B, D, then you start with B, C, you start exploring this, and when you're done exploring C, then you come to B. So it depends on what you've written first. If you've written first B first here, then you should be done exploring B first. Now, if BG was an edge, shouldn't you be writing G here?
Yes.
Because you come to C
Yes.
only when you're done with B. This should not be an edge, right?
Sorry to
Yeah.
interrupt.
Ma'am,
Is
this
there
one
any
is
condition? Is there any condition where we can say no, it cannot be?
Those are the instances that we're discussing. We've discussed all on the same level, then one level jumped, then next level between the immediate levels, this one and this one, the immediate next one. That's all. We're discussing all cases here.
Ma'am, if the tree, ma'am, in this, if the graph was given, if we want to make this tree, the BFS tree on the left, can E and F has
Yeah.
an edge?
E and F, yeah, if you have been given a tree, then E
No,
and F
no.
can have an edge, right? Yeah.
Okay, if we wanted to make a BFS tree left from the graph to right, so E and F can have an edge.
Trees never have an edge that forms a cycle. We discussed this, right? Tree is a connected, it's a maximal
Ma'am,
connected set. Okay.
can you like
Ma'am,
explain
can you just complete what you
from
were saying
start?
first?
Yeah, can you explain it from the start because like
Ma'am, can you
One
just
second.
complete
Yeah.
just what I just asked?
The BFS tree or tree in general is a minimally connected set, right? So minimally connected sets do not have a cycle. They should not have any cycle. So if you will make this edge here in a tree, you can't have this thing because this makes a cycle here. Now this is not a minimally connected thing, not a minimally connected structure. That's why
Okay,
you
ma'am.
cannot
Okay.
have an edge
Okay,
in
ma'am.
simple
That was
words,
just.
no cycles in trees.
So ma'am, basically in BFS we avoid cycles, right?
Not just BFS. It's a tree, that's why we are avoiding a cycle.
Okay, ma'am. Understood. Yes.
Okay. So B and G,
Ma'am,
the answer is no.
on-
And
in the
yes,
tree, we move from left to right, right? So first the vertex B is
yeah,
visited, and then C, and then D.
yeah.
Okay.
Then can we have an edge CF in the original graph? CF.
ma'am, can you explain the
Oh.
tree once more?
Yeah. Let's do this thing first. Can we have an edge from C to F?
No, ma'am.
No, ma'am, we can't.
Okay, let me just
Yes, ma'am.
explain the entire algorithm first again, because I think there's a lot of confusion. What you do in a BFS approach is, let's say you have, let's use ABC.
Ma'am, they're getting confused in which vertex
Yeah.
gets visited first completely.
Let's say you have this thing and you're starting your search from A. You can start it from anywhere, right? I'm starting from A. And you will be given this thing. That's not a choice that you will make in the exam. You will be given this thing. So A is there. You start with A. Then next vertex should be B, C, and D. Now, I hope everyone's clear with the approach. What you do in the approach is you write A. Then next up, if you have this Q, let's make the Q and the tree simultaneous. So if you have A, for the tree you write A here, and in the Q you write A. Then you start exploring A. Exploring means you start visiting every vertex. You write B here, C here, and D here, right? Now you don't have to write them in the same order. You could have written C, B, D. That's up to you.
D won't
Ma'am,
come right.
D is not connected to
Okay,
A.
D is not connected. So CB also you can write. So these two things you can write. Let me just write BC. And then
So,
the
ma'am,
tree
it
will
is
make
sure
B and
that there
C.
is no edge between
Let
A
me just
and D.
complete first. If I won't complete, then how would you understand? So you'll write BC, and when you are done exploring, now you're done because you have visited every vertex directly connected to A. So A is done now, right? You've written A, B, C. Then you come to B. B is directly connected to G. So you have G here, and you write G here. Then B is also done. Coming to C, you have F and D. And then now, yeah, this is a good example. So you're done exploring C, then you come to G. There's nothing to explore from G, so you're done exploring G2. No vertex directly connected to G, right? So G is also done. Then you come to F. Now you have written F and D, right? If I write D and F here, then I'd start with D. And for D, I'll write the E here under D. If this is the order, then I should be making this tree. And if FD is the order, then I should be making this tree. So you go by the
Ma'am,
order. And
if
in
you
this one
change
as
DF,
well,
then even in the tree, the FD will
yeah,
swap,
this
right?
will also change. This will also change.
Okay.
So if you have this thing, then you should have this order. And if you have DF order, then it should be like this: A, B, C, G, D, F, and this should come under D. E should come under D. So the levels, this was level, this is level 2, level 2. Now these things don't change. G, D, F, only the order changes, right? So the vertices don't change on any level. They are the same on every level. Now what we're doing here
Ma'am,
is,
we will given that what order we should take.
you can take any order, that doesn't matter.
Okay.
So when I say if CF is, now can DE be an edge here? Can I have DE as an edge?
Yes.
Yes, ma'am.
You can have DE as an edge, right? Why? Because E was visited
ma'am.
via F first. So it's written here. Doesn't mean I can't have an edge here. But can G and E be an edge?
No, ma'am.
E
Yeah,
and D.
because
No.
I started exploring G first, and when I got done with G, then I came to F. If E was under G, then I should write E here. And I've written it here, right? So go by this order.
Ma'am,
First
here you
this, then
said
this,
that
then this.
E and D can have an edge. You said E and
Yeah,
D,
E and
F.
D can have an edge.
Ma'am, but you
Because
said it becomes cyclic then, ma'am. But cyclic is not like we have to be minimum, na?
H,
Baba, in the
H for the
original
graph, not
graph,
for the tree.
you can have an edge. The question is, everywhere here, the question is, can be an edge in original graph, not the tree. We're talking about the graph. Is that okay?
Yes,
Is
ma'am.
it clear now? Now can CF be an edge? Have a look here and tell can CF be an edge or not.
Yes.
So
CF
CF can be an
cannot.
edge. Why can't CF be an edge? You have already explored, you have already visited F via B. So see, F can also under be C, right? If if F was here, or if you have an edge here,
T2FNH, yes.
if you have an edge here, then what's the problem? You start exploring B first, and F is already visited from there, EF, and you don't repeat vertices in the tree or anywhere for that matter. So you are not supposed to write. If C and F was an edge in original graph, I won't be doing this, right? It can be an edge here. Because C, I'm coming to C later after visiting B. So even if C F was an edge, I would be writing F under B, not C, because I start from here, B, then C, then I come to D. This is the order that I follow.
Remember, you said in tree it cannot be cyclic, so E and F cannot have an edge in the tree. Yes, ma'am?
In the tree, we are not talking about the tree.
Okay.
We're talking about the original graph. Each time I say, can there be an edge? Can there be an edge? It's about the original graph, not the BFS tree. The BFS tree is already given to you. Okay, is this part clear to everyone?
Yes, ma'am.
Then coming to our next topic is DFS1. So let's do one example on DFS. So in DFS, you maintain a stack, and it's in DFS you go to every vertex first, right? If you have A, B, C, D, then you go to every vertex directly connected to A, but that's not what you do here. So if you have this thing here, in DFS search, you start from, let's just say you're starting from here. If this is a graph, let's say this is a graph. A tree is also a graph, by the way. So A, you start with A, then you go to B, and then the next thing won't be C, it will be E here because you come to E next. So going into the depth first, not exploring the breadth. So let's do a proper example on DFS. Let's say you have V1, V2, V3, V4, V5.
There's directed graph.
Yeah, a directed graph you're taking this time. Let's say this is very messed up, I know, but I hope the arrows are clear to everyone where they are pointed. So let's take this graph. If you start with, just give me a minute. Hello? Yeah.
Yeah, ma'am, you are audible.
Let's start our DFS search. Let's start from B1 only. So if you start with B1, the next step is next you should be taking is B2, right? Because that's the only next one. No outgoing vertices, no outgoing edges from B1 other than this, right? So B2 next. Then after V2, it's B6, but we're doing DFS. Right? So after V2, you should take B6. And then after B6, you should take B7.
Ma'am, after
And
taking
then you'll come
V2,
back to V2.
can
Yeah.
we not go to V3? From
Yeah,
V2
you
to
can go to
V3?
V3. You can go to either V3 or V6. Your choice. I've taken V6 here. So you go to V6. Then there's V7. And after V7, you have V2. But V2 has already been done. That means this thing is complete. That means
B7.
V7 is done. We're done exploring V7. That means V7 gets out from here. Then
B6
next up
also.
you take, next up V6 leaves. Then V2. So from V2 you
B3.
come to V3. Then after V3,
B4.
after V3, there's only one possibility, V4. Then V4, you have two possibilities, V5, V8. Let's take V8. And from V8, you go to V7. V7 has been visited. That means you remove V8. Then you remove V4. No,
Oh,
from
ma'am, we'll go
V4,
to
you have a
B5.
possibility, V5. Then you have V5. Then from V5, you have a possibility V1, but V1 is already done. So done exploring V5.
B5 is done.
You come back to
B4 is
V4.
done.
V4 is done. V3
All
is
of them
also done. Yeah, V2 is also done and V1 is also done. That's your DFS approach. And how do you make a DFS tree then? So in a DFS tree, you start with V1, then you write V2, then V6, then V7, and then you trace back to V6. Then from V6 you trace back to V2, and then you make V3 here. Then from V3 you have V4. Then V8.
B4 to B5.
V8 you're done exploring, so you trace back to V4. Then there is V5. And V1 is already done. So this should be your tree, right? Yeah.
Yes.
This is your tree. This time. It's different from a BFS tree, obviously. This is a DFS tree. This is again a tree, so you won't see any cycles here. No cycles is the rule. So this is the DFS approach. And then there's something called keeping the counters for each vertex.
Madam, why
And
V4
this
and
one,
V5 at the same level?
so we don't have the concept of levels here. That was for BFS approach. When we
Okay.
talk about levels, level 1, level 0, this is for DFS only.
Ma'am,
Okay.
can you explain it
In
again?
DFS tree, we don't talk about levels.
Ma'am, can you explain it again, please?
The tree part or the this one, the stack one?
The tree part.
Okay, you start with V1. Then you go to the vertices, that vertex that's directly connected to V1, that has an edge with V1. So V2 has an edge, you write V2 here. Then there are two directions to move in. One is V3, the other one is V6. I've taken V6. An alternate DFS tree could be V1, V2, and then you take V3 here. But then that's the same thing because you go there, and then you come back and then you do the same thing here. Let's do this one first. So you go to V6 then. And after V6, you keep going in the depth, right? You don't explore the breadth, you go in the depth. So from V6 you go to V7. And after V7 you have to go to V2. But V2 has already been visited. So you're not supposed to write V2 here again. Because it's already visited. So from V2, V6, V7. Now, but here is the end, right? So you trace back to V6, then you trace back to V2, and you don't trace back to V1. Then you get done exploring with V2 first, then you trace back. So you only trace back when you're done exploring the vertex, because V7 is done. There is no other vertex connected to V7 that has not already been mentioned in this tree so far, right? If you start with this, then there is no vertex so far that is connected to V7 directly and has not been mentioned yet.
Okay, ma'am.
So you trace
It
back.
means we have to find the depth.
Yeah. You go into the depth, and when you come to this bottom where there's nothing to explore anymore, you trace back. When you're done exploring this, you trace back. Then when you're done exploring this, you trace back. And when you're done exploring this, then you trace back. But you're not done exploring V2 yet. There's V3 left, right? So you write V3 here. Then you go in the depth again. So from V3, you go to V4. And then you go to V8. And after V8, you don't have anywhere else to go. You have V7, but V7 has been visited already. You don't write it again. Then you trace, this is done. That means
Okay,
this has
ma'am.
been explored. So you trace back. V4's not done yet. You have V5 connected to it. So you go to V5. V5 has no other vertices. So V5 is done. Then you trace back to V4, trace back to V3, trace back to V2, and trace back to V1. Is that okay?
Okay, ma'am. Okay.
Yeah, ma'am.
Okay.
Ma'am,
So
this is the property of tree, like it should have like minimum edges in a way.
So not minimum edges exactly. It's a minimally connected, meaning you should, in simple words, you should not have any cycles.
Okay, okay.
So this should not be a thing because it will
Ma'am, in
create a
V4 and
cycle.
V5, like
Yes, ma'am, you
V8
were
is
saying
connected.
something. Can you complete it? What was you saying? Yeah.
Yeah, and you can't have an edge here because that's again a cycle. V6, V2, V3, V4, V6. So this is a cycle. You can't have an edge here.
Okay, so in the
Just
tree we
keep
cannot
these
have a
things in mind.
cycle, whether
Yeah,
it is BFS or DFS.
yeah,
Okay.
because it's a tree.
Okay, ma'am.
In general, in trees, you can't have cycles. Yes.
And V8 is connected to both of V4 and V5. So because we are preventing cycles, so like you have connected V8 to V4, and I can also connect V8 to V5, right?
Yeah, you can. V5, we started with V3, then we went to V4, then V5, and then V8. Actually, that should have been the order. As V8 not been visited already, okay. That should have been the order. If you have V4 here, V5, then because you only trace back when you're done exploring the vertex. So V5 is not done yet, right? I didn't see this edge. V8 should be here. Now you're done exploring V8 because V8 is connected to V3, V7. V3, V7 has been mentioned in the tree already. So you back to V5. Then from V5, V5 is also done. V8, V4, no, V8 and V1, right? V8 and V1 has been mentioned. So V5 is also done. Then you trace back to V4. Then you trace back to V3, then to V2. So it
Okay,
should be
ma'am.
here.
I
There's a
understood.
small correction here. V8 should be under V5
Understood,
because we
ma'am.
weren't
Thank
done
you.
exploring these. Okay.
Ma'am, I have a question. But from V3 we can go to V4. And
Yeah,
from V4 we can go to either V5 or V8.
yeah. The both of the trees are correct actually.
Okay.
That's we have an edge here too. Then. Okay, let me just clear up the confusion if there is any. You can make this. This is also a DFS tree, and the other one that I made. This one. Correct it here. Because V4, if you write
Ma'am,
V8
before
first, no, what happens? You go to V4. We weren't done exploring V5. We were done exploring V8. This was done. You came to V4.
Yes, ma'am.
Then you went to V8 directly. And then with V8 we were done. So we traced back and then went there. So both of these trees are DFS trees for the same graph. Both of these are correct. Is that okay?
yes,
Yeah,
ma'am.
ma'am.
Can I see the graph for a minute?
Ma'am, in the lecture, in the DFS tree, there is pre and post number assigned to every vertex.
Yeah, we'll do that. So should we do one more example on DFS depth first search, or is this one enough? Should we come to the counter one?
Ma'am, I guess it's enough.
It is a-
It's fine. You can move forward.
So next up we have the non-edge non-tree edges. So non-tree edges are basically, for that we'll have to discuss the counter thing. So non-tree edges are basically the edges in the original graph that are not an edge in the tree. So this is your DFS tree, right? This is your DFS graph, and no, this is just a graph. Sorry, this is a graph, and this is your DFS tree. So there are two types of edges here, classified in two categories. One are tree edges. So the V1, V2 is a tree edge in this. Why? Because it's in the tree. So every edge that's in the tree is a tree edge in this graph, and every other edge which is not in this DFS tree are called non-tree edges. And there are three. They are categorized into three. So forward, back, and cross edge are there. Forward edge, back edge, and cross edge. So let's first discuss the counters, and then we will discuss these edges. And let's take this example only. So when we were making the tree, we can keep a counter. Let's draw this tree again, then it will be clear how we have to keep the counter in the sense, a counter of when you visited the vertex and when you got done exploring with the vertex. In what order, right? That's a counter here. So we started with B1. So we keep the this is the initial counter from where you start. That's that counter when you number the vertex when you first visited the vertex. So when you visit the vertex, you put this 0. So first you visited B1 because you're starting your search from B1. So you put a 0 here. And when you're done exploring this vertex, then you put the end counter here. That you started at 0. Then you have B2. So we put a 1 here because for B2 you started at 1. 0, 1. Then B6. This has 2. Then B7, this has 3. I should just circle this number. This number is the initial counter. Initial counter in the sense you started with the vertex at number 0. Then the next is this. Next step you did this. 1, then 2, then 3. And then you're done exploring and you put the end counter when you're done exploring the vertex. Done exploring means when you visited all the vertices directly connected to that vertex is when you put the end counter. So after 3, this is on number 3, right? B7 has nowhere to go to. That means you're done exploring this vertex. So you put an end counter here, 4. So you, in simple words, you put an end counter when you trace back from that vertex. And when do you trace back? When you're done exploring that vertex. So this will have an end counter 4. Then you'll come to V6. And you're also done exploring V6. So that will give this an end counter 5. Then you'll come to V2. But we're not done exploring V2. So we can't put an end counter here because we're not done exploring V2. We come to V3 and we put an initial counter 6. Then we come to V4, initial counter 7. Then we come to let's say we come to V5, initial counter 8. Then V8, initial counter 9. And because there's nowhere to go to from V8, so the counter closes here on 10. Then you trace back. This is also explored, so you put an end counter 11. This is also explored, so you put 12 here. Then you put 13 here. Then exploring this too, so you put 14 here, and then 15 here. Is this thing okay?
Yeah, ma'am.
Yeah, ma'am.
Ma'am, that's
Ma'am,
basically
I
your
have a
numbering.
doubt. Yeah, I have a slight doubt that like in the tree we can place B7 like B3 to B7.
V3 to V7.
Yeah.
If you start with V3 first, if you'll do this thing, V1, V2, and then you'll write V3. So if you have turned to V3, then you'll get done with V3 obviously. So you'll write V7 under this.
And
That's right.
if we put V2 like V3 and V6 and we'll mark V3 to V7.
You're
Yeah,
suggesting
B4.
6 here.
Can we do that here? Yeah, and by V2 we have V3. Like we have V2 connected with V3 and V3 connected with V7 and V4. V4 and V7.
Can't do that. Once you started going in this direction, then you can't come back until you're done with this direction. Or if you've started going in this direction, that's what I was explaining. If you have decided to go in this direction, then that's okay. You start with V1, V2, V3, and then you go to V7. That's fine.
Ma'am, you are
Yeah,
numbering them just as a symbol that you have done tracing back for that reason.
What?
You are numbering them, no? The tree. So,
Yeah.
like for the what purpose you are numbering? Like you have done tracing back for that.
Yeah, when you visit the vertex first, you put an initial counter here, and when you are done exploring that vertex, you put the end counter, whatever that
Okay,
counter is.
Ma'am, when we are
Understood.
making a tree from a graph, so every edge in the tree should be in the graph now, but not the vice versa.
Yeah,
Like,
what?
like every edge in the tree should be in the graph now, ma'am.
Yeah, every edge in the tree should be in the graph.
But not the vice versa, na, ma'am.
No.
Okay, ma'am.
Ma'am, just a question. So
Yeah,
so the counter really tells us like in how many steps we can explore the whole tree. Depth,
Yeah.
according to depth first search, correct?
Yeah, it does tell you that. There are other reasons and other applications of it. One of the application is your edges, type of non-tree edges.
Okay.
So let's draw this carefully. Your non-tree edges basically are classified in three. One is forward edge, then your back edge, and then cross edge. So forward edges are, one second. Yeah, these are the numbers. So forward edge is basically because you have this thing here. It's now if this closes this thing, then this is a back edge. We're obviously going in this direction, right? We first came from here to here, this direction, then this direction. So now if this was an edge in the original graph, right? This can be an edge, right? If you have the original graph, this is the original graph. But if we can make some other graph, in some other graph, can this be a possible edge? If this is your DFS tree.
Yeah, it can be.
It can be, right? So if this was an edge,
Ma'am,
this
you can
would be
explain V4 to V1. It's there in the graph. That'll be easier.
V4 to V1. V4 to V1 is already there. So now if you have this edge, this would have been a little easier to understand because it directly shows you how this cycle is being formed. So this is the cycle, right? This
Ma'am, how
from
V3
V1,
to V1 can be an edge? Because in the original graph there is no edge.
original graph, there is no edge, but there could be other graphs corresponding to which this is the DFS tree, right? DFS tree, the original graph for a DFS tree is not unique. So this is not the only graph that can have this DFS tree. There are other graphs too that
Okay,
can have
ma'am.
the same
Okay.
DFS tree.
Okay, ma'am. Okay.
We're talking about if there is any graph out there which can have this as its DFS tree. That's what we're talking about. And then can this be an edge there? So if you have this thing, then V1 to V2 to V3 to V4 and then back to V1. This is a cycle, right? You started with V1, ended with V1. This makes a cycle, right?
Yes, ma'am.
So this
Yeah,
is
ma'am.
the edges that make a cycle. So we know that there are some edges in this. This is your graph, and this is your DFS tree. So in your original graph, there are some edges that are not present in the DFS tree, and this V4 to V1 edge is one of those edges, right? V4 to V1 is an edge which is present in the graph, but it's not present in your tree. That's why it's a non-tree edge. And what kind of non-tree edge is it? It's a back edge because it's completing a cycle. So any edge that completes a cycle is a back edge.
Ma'am, but how you make an edge from V4 to V1?
There already is an edge here, V4 to V1 in the original graph.
Yes, ma'am.
That's why this is a non-tree edge. We're not making any edge in the DFS tree. We just make
Okay,
it with dotted line.
from the
Yeah.
reference of graph, we made it in a way.
Yeah, I'm
Completing
just
the
doing this.
original graph by showing it
I'm
in
just
different.
doing this for you to see that there is a cycle here. That's it. This edge forms a cycle. This is an edge in the original graph, and this forms a cycle. Doesn't mean it's an edge in the tree. So back edges are the ones that complete the cycle, and forward edges are if your original graph was like this. Let's remove this thing and let's make this V1 to V4 instead. Then the direction would be this, right? Then because now this is no more a cycle. This edge is opposing the cycle. That's why it's a forward edge. Then your V1 to V4 would be a forward edge. And if say you have both, you have this edge, your graph directed in this order. V1 to V4 is also an edge, V4 to V1 is also an edge. V1 to V4 is an edge in the original graph, but it's not in the tree. That's why it's a non-tree edge. And what sort of non-tree edge is it? Because it's completing a cycle. No, not completing a cycle. V1 to V4 is not completing a cycle. It's opposing the cycle. The cycle was to be formed from here, but it's opposing a cycle. That's why it's a forward edge. And V4 to V1 in the original graph is again a non-tree edge, and it's the back edge. And by the very definition of it, how do we identify if it's a using the counter? We identify it in this manner. So we first write the
How you draw this
one
V1 to V4?
Yes.
Is there any edge in the original graph V1 to V4?
Yeah, I've drawn it later for
Okay,
you
okay.
people to understand.
So, ma'am, to make a non-tree edges, we have to see the reference from the original graph, na?
I'm writing the definition here, the proper definition of what a back edge, a cross edge, and a forward edge is. So for a back, let's start with forward edge first. So for a forward edge, let's say you have an edge UV. Then UV is the forward edge. If the tree number means this one, the one that you write on the left side. The pre number of V and the post number of V. If this interval, this is an interval, right? Like in this one, we'll do it for V1 and V4. Wait. If this is contained in pre-post number for U, then it's a forward edge. For example, in this one, we say this is a forward edge. Let's just check this definition for this vertex, V1 to this edge, V1 to V4, right? The pre number for V1 is there, it's 0 to 15, right? And the post number for V4 is
712.
V post number is 7 to 12. So it's 7 to 12. That means this thing is contained in this. 7 to 12 is contained in 0 to 15. So, and we're taking V1 to V4. So, V1 to V4 is a forward edge, right? 1 second.
Ma'am, these numbers will not work for forward edge because then you have to go back to 1 and then come back to 5. I think
0 to 15 if this is, and then I think it's the opposite. I think you have U here
backward edge, yes.
and B here. This is the definition for forward edge.
What is the sign that you have put between 015 and 712? It's the sub that. What is the sign?
This is contained.
Okay.
Containment symbol.
Okay, ma'am.
So if you see this again, if you have this edge, forward edge is basically how do you come to this definition? Because you start with 015 and then 712, because that 712 if is contained in 015, that means you visited this thing later after V1, right? That means V1 is a parent of V4, not a direct parent, it's an ancestor of V4. Parents are basically the V3 is a parent of V4, V2 is parent of V3, and V1 is ancestor of V2, V3, and V4, all of these later. That's ancestor, parent, child classification. So this also helps you which edge is coming, which vertex is coming from which vertex. So if you have V1 to V4, you start with U, right? So pre-number, post-number of V1, V2. No, we did the right thing, I think. It should be V only here. We made a mistake in this part, I guess. So if you have pre-number, post-number for V for the later one, right? For the second one. So pre-number, post-number for V4 is 7 to 12. We made a mistake here. It's 7 to 12. Pre-number, post-number of this one first, right? We first write for V. So this, and then pre-number, post-number for U, which is V1. So it's 0 to 15. Because this is contained in this, that means it's a forward edge. So this thing is a forward edge in the original graphs. Let's take V4 to V1. And for the back edge, the definition is UV is a back edge if it's the opposite of this. Pre-U, post-U is contained in pre-V, post-V.
Ma'am, in the forward, you have written pre-V, post-V, contained in pre-U, post-U or post-V? It's
U.
okay.
Basically, you're just testing the bigger the if this interval is contained in this interval. For example, 613 is contained in 015, right? That means you started with this vertex first, and then you came to this vertex, got done with this vertex first, and then got done with this vertex, right? That's why this interval contains this interval. And that's why you have a forward edge from here to here. Is that okay?
Yeah. Ma'am, like there is, it is written like pre-U, post-U.
Yeah.
Yeah, you have written like pre-V, post-V, and then like contains pre-U, post-U.
Yeah, this is for back one, and that one is for forward one.
Then is
In the
that V was connected
in
to
the
all the other vertices through forward edge.
What?
yeah, ma'am. Let me complete. Like pre-U, ma'am. Is it right? we don't write V here. Like pre-U and post-U, we write only U.
Can
What's
you
your
also just
question? I
write,
don't understand.
ma'am, can you also write just in a way you have
One
given the
second,
example
let's
in
get done with her doubt first. What was it?
Ma'am, in the back, just scroll little up. Yeah, so you write for forward U comma V, pre-V, post V contains pre-U and post-U.
Yeah.
So we have to take like pre-V and post-V, and then pre-U and post-U.
You just have to check this statement, this inequality, this you have to check. If this interval, this is an interval, right? Pre-V, post-V, you check from here. V1 in this, if you do this example V1 to V4, first you check V4 because V4 is in place of V, right? So V4 is this 7 to 12. You write 7 to 12 here, then you come to V1. For V1, it's 0 to 15. You write 0 to 15 here, and then you check whether this one, the one for V4, the later one, second one, if this is contained in the interval for the first one, V1. Is that okay?
Okay, ma'am.
Ma'am, then is it that V1 contains, I mean, it is indirectly connected to all the other vertices through a forward edge?
No, it doesn't mean it's connected to all the vertices. What we're doing here is, okay, when you have a graph, this is a graph, right? And this is a tree for the same graph. Now there are some edges in this graph that are not there in this tree. I can't make an edge from V1 to V6 because that's not an edge in the original graph. This tree does not mean that you can have a forward edge from V1 to anywhere because there's no edge. There are, like, you can't have an edge from V1 to everywhere. Are there edges from V1 to everywhere in this graph? You don't have a direct edge.
No, ma'am.
You don't have an edge from V1 to V. This is V8. V1 to V8. That means there can't be a forward edge from V1 to V8 because there is no edge from V1 to V8 in the graph. So this tree is just, this is graphs. When you make a tree, firstly you follow the DFS approach, and then you just make sure for this to be a tree, there should be no cycles. That's all. And then there are some edges in this graph that are not there in this tree. Those are called non-tree edges. And they're
Ma'am,
classified into three: forward edge, back edge, cross edge. These two we've already done, forward, back, and cross edge. Let me just write down the definition for that.
ma'am, one thing for the forward, when you wrote 712 containing 015, so it's an arrow from 4 to 1, ma'am, in the tree. The
In
arrow
the
is
tree,
going
I've
from,
modified this thing. I modified it later.
yeah. But if it is only going upward, we have to make a arrow from in the tree. We have to make an arrow from
You don't
V4
make
to,
an arrow in the tree. What's given to you, you don't manipulate that thing. Don't change the question. If this arrow is given as this only, I
suppose
am
there is
changing
an,
these things to avoid doing a lot of making this graph again and
yes,
explaining
ma'am.
things
I was
again.
saying, ma'am, non-tree edges. If we want to make a non-tree edge in the DFS tree, so the arrow should go from V4 to V1. Na? That would be a forward
Yeah,
non-tree edge. That was my thing.
that's not forward. V4 to V1 is a back edge.
Okay. Okay. So the forward would be 712 to 015. We write in that way. 712 contain in
If you have
015.
V1, V4, and
Yeah.
V1 is a parent of V4, then it's a forward edge. If
Yeah,
V4 is
ma'am.
a parent of V1, then that's a back edge. Is that okay?
Just repeat, ma'am. Just.
Ma'am, if the graph is not given and only the DFS tree is given, then how should we find it out?
You won't be given questions like that. If you're just given the DFS tree and you've been asked, then you'll be told that V1, V4 is an edge in the original graph, right?
Yeah, ma'am.
Okay,
You
ma'am.
were saying something.
V1 to V4, if you have been given the edge is V1, V4, that means it starts from V1, it's directed towards V4. Now, if
That a
V1 is a parent of V4, then it's a forward edge.
forward tree edge in a way.
not forward tree edge. It's called a forward edge.
Yeah, ma'am. Ma'am, I was talking about the forward tree edge when you rotate.
Yeah.
Yeah, when you rotate, just if you go a little back, when
Yeah.
you rotate, yeah, when you rotate like 712 contain in 015, you make it in a forward edge. Yeah, ma'am. So that
Yeah.
forward edge in the tree is going from 712 to 015 in a way. Okay,
Yeah.
it's
It's
going.
going to 7. Yeah,
So
it's
that
not
means
going there. You're just
okay,
checking. You're
okay,
checking this to make sure that this thing comes later. That's
okay.
how
So
you
it is.
decide that this
So
is the
it is.
parent of this, right?
Yeah, ma'am. So it is the forward tree edge is going from 015 to 712 in a way. But we
Don't put
write
it
in
0.
but we write it in different way. I'm saying that na in reverse.
It is written, it is not written that it is visited after V1. It is written that V 712 is contains 015.
So that's a forward edge, na ma'am. That's what I wanted to say.
Because 712 is contained in 015. That's why you can ensure that this vertex was visited after this vertex.
Okay.
So if this is V, this is U, and you have this VU. Now what edge is this?
It's a forward tree edge.
Yeah, it is forward tree edge.
V, you have 015. So 015 to this, you have a forward edge. This is the forward edge. And the other one, because this is the bigger one is the parent. And if obviously the bigger interval is the parent, right? Because you started with that vertex first.
Okay, the parent edge would be written after it. Okay,
Yeah.
that was
And
my
not,
that was my issue.
I should be saying ancestor because it's not a direct parent. V1 is not a parent of V4, it's an ancestor of V4. But it doesn't matter. The idea here is that this is the bigger interval is the parent. So if you write from this to this, then that means you're writing the child first and then the ancestor. So it's a back edge. But if you write this to this, that means you're writing the parent first. That's what I was explaining here. If you write the parent first and then or the ancestor first and then the child or this vertex later. So if the ancestor is written first, then it's a forward edge. If your ancestor is written later, then it's a back edge. That's all. And that you check using the intervals. Ancestor and parent you can only recognize using the intervals. And in the cross edges, you have pre-U, post-U. An intersection with pre-V, post-V, empty. So if you have this intersection empty, that means this counter, initial and ending, does not have anything to do with this counter. For example, let's say if you have UV and U starts from 0 to 5, this interval, and V is from 6 to 7, let's say, then the intersection is empty. That means if this is an edge there, then it's a cross edge. For example, this one, if in this entire tree, if you have this thing 2 to 5 and then 7 to 12, now this will be a cross edge. Because 2 to 5 interval, if it is an edge in the original graph, then it's a cross edge. If it's not an edge, then it's nothing. Right? So if V6, V4 is not an edge, do we have an example of V7?
Kind of connecting two branches, no?
Yeah, this one and this one, are they somehow connected? In V4
V8,
and here is
V7.
V6, V7, V8. V8. V7, V8 is an edge here, and it's not an edge. That means it comes under the non-tree edges. And under non-tree edges, it's a cross edge. In particular, it's a cross edge because 3 to 4 interval has nothing to do with this interval, 9 to 10. This is 9 to 10. Intersection of 3, 4 interval and 9, 10 interval is empty. That's why this edge is a cross edge. V8 to V7 edge is a cross edge. Now, when I say V8 to V7, obviously this is not an edge in the tree, it's an edge in the graph. So V8 to V7 is a cross edge in the graph. Is that okay?
Yes, ma'am.
Ma'am, one thing in the forward, you told that ancestor should be written first, na? And then the child should be written.
Yeah.
But in the forward, when you wrote it, you wrote child first in the example. 7, 12, 0, 15. So it should be 0, 15, 7, 12, na?
In the
The
forward
first
one,
is UV. It's
forward,
UV
you
that
write
is first and second.
Ancestor first, na, ma'am? So ancestor is 0, 15.
Ma'am told you about V1 and V4, not 7, 12, and 0, 15.
It's an example
Yeah.
of forward edge, na, ma'am?
This is for V4. This is for V1. Now from V4 to V1, you have a, and the edge is V1 to V4. We're not talking about the edge V4 to V2. We are talking about the edge V1 to V4.
Okay, so it's written in a way V1 is an ancestor edge and V4 is a child edge. But we wrote it in a way V4 contained in V1. In that way you wrote it. You're saying that. V1 is an ancestral edge, na, ma'am?
V1 comes first and
Yeah,
V1
ma'am.
is here. So I
Okay,
said
ma'am.
that the parent one should be containing the, or the ancestor one should interval, ancestor interval should be containing this interval. Is it not containing this interval?
Yeah, ma'am, it is containing. Okay, ma'am.
What's the problem? I said this interval should be the bigger one. That's it.
Okay.
Ma'am, can you just explain the definition of cross edge once again?
In cross edges, back edges and forward edges, you need contained. Either this is contained in this or this is contained in this. Then you have a cross back edge or forward edge, depending on containment. And in cross edge, these two intervals they should not be containing points of each other. That means the intersection should be empty. That's all. So your pre-U post-U should have no common points from here. For example, if there is an edge UB and the starting and ending points of U are 0 to 5 and the starting and ending points of V are 6 to 7. These two intervals don't have anything in common, right? So if this is an edge in a graph, then this is a cross edge. This is an example of cross edge. In our original graph, in this graph, we have V7 to V8. So V8 to V7 is an edge, right? Now it's
Yes, ma'am.
V8 to V7 is in the graph, but it's not in the tree. That means it's a non-tree edge, right? And if you look at the counters here, for V7 it's 3 to 4, and for V8 it's 9 to 10. Here. And 3, 4 is not contained in this. This is not contained in this. In fact, the intersection is empty. That's why it's a cross edge. So V8 to V7 is a cross edge.
Okay.
Is that okay? Okay. Then we have cut vertices. So cut vertices are basically the vertices which when removed makes the graph disconnected. So if you remove one vertex, the graph will become disconnected. Those vertices are called cut vertices. And then you have cut edges called bridges.
In the case of cross edge, what should be the direction, like forward or backward?
If you have this thing, the direction is already in this graph. Now, why do you need the direction?
No, like we can V8 to
You don't
V7
decide the
in the graph.
direction. If in this
Okay.
graph, if you look at it, you can't decide V1 to V4 or V4 to V1. It's already decided in the graph. It's V4 to V1. So you will be asked, is V4, V1 a forward edge, back edge, or a cross edge? Right? So this is what you're going to be asked. Similarly, you can be asked V8 to V7 because that's the original edge in the graph, right? Is this a forward edge, back edge, or cross edge? Is that okay?
Okay, so for the cross edge, we just have to know that there would be no intersection. Like
Yeah.
that is the end. Yeah.
Yeah. The direction is already decided in the graph. Okay. And coming to cut vertices are vertices which, when removed from the graph, make the graph disconnected. For example, let's say you have this graph and this thing. Now, if I remove this vertex, the graph will be left, or let's first do the bridges.
Ma'am?
Yeah. So cut vertices are the vertices that make your graph disconnected. Let's say you have this vertex, and if you remove one vertex from there, from somewhere, if this vertex is removed, then your graph becomes disconnected. That's called the cut vertex. And your cut edges, also called bridges, are the edges which, when removed from the graph, makes the graph disconnected. So if I remove which are the edges that are going to make this graph disconnected? Uh, 1, V2, V3, V4, V5, V6. Let's not mention them, it's not that important. It's just a basic thing, basic definition that you should know. So if I remove, for example, if I remove this edge, then this graph becomes disconnected. So it's a cut edge or a bridge. If I remove this edge, then also it becomes disconnected. This is also a bridge. Now if I remove this one, then what's going to happen?
Then also it will be a cut.
Happen.
Yeah, because there's a vertex, it will be left alone. So then also it's a bridge. I hope the definition of cut vertices and bridges is clear. And then next we have and then we have DAG, directed acyclic graph. Directed acyclic graph is a graph which is a directed graph, and it's acyclic. So what's a directed graph? Which has directions, right?
Yeah, ma'am.
Yes.
That's a directed graph. 1 second. And then an acyclic graph is which does not have any cycles, right? This is not an acyclic graph. Lots of cycles there. And this we can, if carefully choosing, it can be made into a. Now it's an acyclic graph, right? That's
Ma'am,
and
it
then
could
we
be a
take these
tree,
trees
right?
together. Yeah, this can be a tree too. Acyclic graphs are trees. So let's not go there. So DAG is basically a directed graph which is acyclic. That means no cycles there, right? So and then using this DAG thing, we do the topological sorting. So what is topological sorting?
Ma'am, this graph, the cycle is there, right? At the end? The triangle one?
And it's not even acyclic. Now it's acyclic.
Okay.
So
Ma'am,
this is acyclic.
directed acyclic graph can be both DFS and BFS tree also, no?
Yeah, the DFS and BFS trees are directed acyclic graphs. But they should have directions.
Okay, ma'am.
In topological sorting, what you do is topological sorting is basically identifying the dependencies. Like let's say you have a graph V1, V2, V3, V4. One second. Let's say you have a graph, this thing, and then if you have directions here, and let's consider these to be subjects. Let's say these are your subjects. V1, V2, V3 are subjects that you're studying. So, and these are dependencies, let's say. That means you have to get done with V1 subject in order to start with V2 subject. This arrow means when you have V1 to V2, this means that in order to start with V2 subject, you need to get done with V1 subject. In order to get done with V1 subject, you need to get done with V3. And in order to get done with V4, you need to get done with V2. So if this is your graph, and if these are the dependencies, then can I have this? Can I have an arrow like this in this? Where V3 goes to V5, V5 goes to V3 again.
Ma'am, but this is not acyclic, right?
Let's forget about acyclic and all for a second, and let's see if dependencies can go this way. That
No, ma'am,
means
it
when I
can't
draw
be.
this thing, why can't it go this way?
Because it will create cycle. Both are depending on.
Let's forget about the cycle. This
मैम
edge is
बिकॉज
creating a
टू
problem.
मैम
Even
V5
if,
तक पहुंचने में
Both are
V4 चाहिएगा
depending
V4
upon.
V3 like
yeah,
V4 is essential to go through V5 because there is an arrow from V4 to V3 so
and
it
you
can't
don't even have to get, yeah, there's a cycle there. That's one problem. And this edge is also a problem, right? V3 is required for V5, V5 is required for V3. So you can't just start.
yes ma'am
So this should not be here. And then in this cycle is also a problem. For V2, you require this. This is literally a cycle. So that means you require all the subjects, or there's no starting point from where you should be starting. What should you study first, right? So we should remove at least one of these. Let's say I remove this. What now?
yes ma'am now we can put maybe forward
V5.
backward
We can start from
Now it's
V5.
fine. And
But
if
what
I do
about
this thing,
V3, madam? Like how V3 connected to V1? Like it's a directed graph, right?
yeah.
Start from
Until I
V3.
complete V3, I cannot go to V1. So that's again problem.
Yeah, so you start with V3 then.
But how can I start V3 because it's not connected to V4, right?
You
And I
don't
cannot
have to
start.
start with the one that is connected to everything. So my idea was, this was just a simple example where I said that these are subjects, and for this subject, these are dependencies, right? So you can start with V3 subject. You can start studying with V3. You can start with this subject.
Okay,
Start
V3
studying this
first.
subject. V3 first, and then you can do whatever's there. V4,
Okay.
V1, then V2, V4. You can start these two simultaneously because they don't have to do, they don't have anything to do with each other, right? They're not required for each other. So you can start them simultaneously. Okay. So that's what topological sorting does.
ma'am you
Topological
were
sorting
trying to
means
say that
you,
we can have a both arrow in V3 and V5 both
yeah,
two
if
arrows
you can't have two arrows anywhere in this graph. So if you want to topologically sort things, topologically sorting these events mean you write them in an order of dependency. That means you start with V3. Now V3 does not depend on anything, so you should start with V3. Then you go to V1, then V2, then V4, and then V5. Or you can actually V5 and V1 can be done simultaneously, but because we can't make it like this, V1 and V5 together. So we're doing it this way, right? So this is fine. In fact, you can put V5 somewhere else too. You can put V5 directly after V1. In this order, if you start studying the subjects in this order, then there'll be no problem, right? Now, if I'll draw one arrow, this double arrow, then that means V3 is required for V5, V5 is required for V3. So where should I start then? Should I start studying V3 first or V5 first? If there are both these arrows, then where should I start from?
Can't we take both
Either.
of them?
V5.
then?
There is
V5
no
we have
start
to start,
point.
right?
Can't start then.
There is start point.
There's no way you can start studying because you require, and that's not even possible. If you require V3, there are no subjects then it will be just one subject.
And
So
when you made
that's why that's exactly the same problem with cycles too. If you had this cycle, then the problem would be from V1 you can go to V2. So from V2 you require V1. For V4 you require V2, and for V3 you require V1. And then this requires V1. I'm sorry. This is V4, V3. So it's this.
Ma'am, in that topological sorting, you have written V3. V1 requires V3, V2 requires V1, V4 requires V2. Then you have written that V5. Does this mean that V5 required V4 to be complete?
Yeah, V5 requires V4, but this arrow was not there initially. I've just made this for you to understand why a cycle is problem, for you to
No,
logically
ma'am.
solve.
I'm not talking about that one in the bottom one.
Okay.
That V3 to V1, V1 to V2, V1, V2 to V4, then V4 to V5.
This was as per this. When you had this thing, that's when I wrote this thing.
Yes, ma'am. But if we have written the V5 at the end, does this mean that V5 requires V4 to complete to be
No, this
completed?
is not requirement. This is the order that you can do the tasks in or do the subjects in. These are just orders that you can start with. That's why I said you can start with V3 subject, then you can do V1, then you can do V2, V3. This is just the order in which you should be studying the subjects. That's all.
Ma'am,
You can
can't
also
put
do this.
V5
V3
after
to V5.
ma'am,
You can.
ma'am.
And I already mentioned it that you can put V5 somewhere else.
Okay, ma'am.
But just don't put it before V3 because you require V3 for V5. Else you
But
can put
ma'am,
V5
there
in
is
V1.
no edge between V4 to V5. So how we do that?
This is not about edges. I was just trying to give you an idea of what is topological sorting and why is it required. It's required for you to identify dependencies in the sense V5. Now this means this is for dependency, right? You have arrows and arrows
Ma'am,
represent
V5 is
dependencies.
dependent.
So
V5 is
this is not
dependent
for
for
V3.
V3.
If you let me
V3, right?
speak, then only I can explain things, right? This
Okay,
thing
ma'am.
is not for dependency. This is the order in which you study the subjects. That's all. Can I go in this order? Is it okay? If there's a student,
Yes, ma'am. We can
and
go in this order.
the student knows that I require the subjects as per this graph, then can that student start studying V3 and then V5, V1, V2, V4? Is there a problem?
No, ma'am.
It doesn't mean V5 require all of the ones or V5 is required by all of these that come after it. We don't mean that.
Yes, ma'am.
We're just
Understood.
trying to find an order. That's all.
Here, ma'am, V5 can be second also and last also, but not
Yeah, it could
anywhere
be
else.
last. You can't the only problem is you can't take V5 before V3. That's all. Because
Yes,
if you
ma'am.
start studying, you can't start studying with V5. You require V3 for that. So
But V5 can be put anywhere else. That's fine.
anywhere else you can put. That's
Okay,
fine.
ma'am.
So basically, we can't put like child before parent.
Yeah, you can say that. This is called topological sorting. So there could be other examples like attending classes or the subjects that you require for, or in the standards and the classes that you study in school, first, second, third. So those are directly related to each other. So there's only one way to go about it, which is do first, then second, then third. You can't just change the order. Here you can have different orders because the dependencies are different. But in your school, you have very straightforward dependencies, right? That is also one case of topological sorting only. And then what do these two have to do with each other? So DAG is a directly acyclic graph, and we have this thing. So if your graph is a DAG, then only it can be topologically sorted. Else you can't topologically sort it.
The last
That
line,
means
what did you
if
say?
you have a graph, and it is topologically sorted, or you can sort it topologically, then it should be DAG. And if it's a DAG, then it can be sorted topologically. That's all. Goes both ways. That means if DAG in the sense, and why does this happen? Because DAG means directed. So obviously you need directions for topological sorting, right? Let's do this first. You need directions for topological sorting. If you need to sort this thing, sorting means you have to decide the order in which you should be doing the subjects, right? That's what topologically sorting means. If you can topologically sort a graph, that means there's a direction, right? If there were no directions, then how would you find the dependencies? That means it's a directed graph. And then it should be acyclic. So we just saw that if you take a cyclic graph here, then it can't be sorted topologically, right?
Yes, ma'am.
That means if you can topologically sort a graph, then it should be acyclic, right? That means every graph that can be topologically sorted is a DAG. And if it's a DAG, that means it's directed and it's acyclic, then you can topologically sort it. You can
So
find this thing.
topologically sorted just means what you did V3, V1, V2, V4, V5, giving a direction for
That's called topological
horizontal.
sorting.
Okay, ma'am.
Yeah. But how do you do it? This was a very simple graph. That's why there's no problem. But there are graphs where there are a lot of dependencies. So let's do one example on that.
So there could be multiple ways to topological sort, right?
There are multiple ways to sort it. So first thing that you do is, I'm looking for a graph to explain things. Just 1 second. Let's take this graph. Let's say you have V1 here. Let's write 1, 2, 3 only. 1, 2, 4. These are important for you to topologically sort to this direction. Then 10, 9, let's take this and this. So let's say this is your graph and you want to topologically sort it. So you should be start with which point should I be starting from? The one that has no incoming arrows is the one I should be starting with, right? Because that's the one where there are no dependencies. That means, for example, this one. One is not dependent on anything. So you can start with one. So if there are no incoming arrows, then you can start with that vertex. One such example is 1.
Ma'am, can we
Are there
start
any?
with 9 also? No.
9 you can't start with. 9 is at the end and there is an arrow incoming.
Okay.
You can also start with 2 in this case because 2 has no incoming arrows. You
Ma'am,
can
2
start
has an
with 2.
incoming arrow from 1
Two
now.
has one incoming arrow.
Yeah, okay, 1
Yeah,
has,
one.
I thought it's this way.
I have to start only from 1 because 1 is the only
Yeah.
vertex which is having incoming arrows.
This is the only vertex, I guess. Yeah, all the other ones are dependent on something else. So we'll start with 1. And next up,
Yeah, cyclic is there, right?
It's not
no,
cyclic
no
actually.
cycles. There are no cycles.
2
For
and 3,
cycle, you need,
2 and 3 are connected, right?
they are connected.
Yeah, ma'am. It's cyclic.
Ma'am, it's not
It's
cyclic
not
because it's
cyclic. It's cycle. For
No, you
cycle, you
cannot
need
go
to do
back.
thing.
Cannot go
like
clockwise, anti-clockwise.
it could be cyclic when there is an incoming arrow from 3 to 2, but it's not that.
Okay.
Yeah,
Okay. Sorry.
this should be the case. It should be a closed thing here, like this, a closed loop. An arrow should be according to that thing only. So this one is not cyclic.
Ma'am, 2 to 5, 5 to 8, and like 2 is also going to
So you
8.
can take 2. You can also take 4, but let's start with 2. And then you can take 5, 6. And let's not do it this way. Let's start with this. So there's a proper way to do things instead of just going with the flow. So you write all the in degrees of the vertices. So in degree of this is 0. In degree of this is 1. In degree of this is also 1. In degree of this is 2.
2.
For this it's 1.
1, 1.
This is also 1. Then this one
1.
is also 1. This
1.
one's also 1. This
2.
is 3.
3.
And
2.
this one
Ma'am, in
is,
degrees, how many arrows it is coming?
yeah, in degree is the number
It
of
has
arrows
2.
pointing towards it.
It is 2,
1,
ma'am.
It
2, and
has
5.
2. And 2 we are already done with. So these are the in degrees. And then you start with this. So you remove this thing first. So 1 you write here and you remove 1 from here. So remove this thing and these arrows too. Then obviously the in degree of 4 and 2 will be affected. So this will become 0 and this will also become 0. So the next you'll decide as per the least in the 0 one, right? So both of them are 0. You can choose any one of them. So you can take 2 and then you can remove 2 and all the arrows that are pointed from 2. This arrow you can remove. This also you can remove. And this also you can remove. And change the in degrees too. This will become 0. No, it should have been 2, right?
And that won't change.
Was
1.
it connected? Yeah, it wasn't connected to 2, right?
It wasn't connected to 2.
Okay. So this and
In
wait,
degree
which ones were
3
the
will become 1.
All the 2's, ma'am. 3 and 8.
And
2
5 will
was there and it was
And
connected to
7.
5, 8, 7, right?
Yes.
5, 8, 7 and it was connected to 3.
3 and 8 also.
So the in degree of this will change. This will become 1. In degree of 5 will change. This will become 0. In degree of 7 will change. It will become 2. In degree of 8 will change. It will become 1. So now you have this. And then you can go in this direction or you can put 4 here too. So you can choose 4 or 5, whatever you want. You can put 5 and then remove this thing. So if I remove this arrow, this will become 0. And this arrow, this will also become 0. And then next up, you can take any of these three, 4, 8, and 6. Let's take 6. If I remove this, the in degree will become 1 here. Next up, you can take 8. This thing will become 0 then. Now you can take any one of these two. Then I'm going with the flow, so I'm taking 7 here, but you can take 4 too. That's your choice. And this is also done. And then now that 0 in degree is only for 4, so 4 next. Then you remove 4 and this. So 3 then. And then next you can take 10, 9 or 9, 10, anyone. Right? This will be the topological sorting order, and it's not unique, it can be changed. We just saw that there were a lot of options that had in degree 0. So you could start with any one of them. But that's how to topologically sort graphs.
So, ma'am, cyclic graph cannot be sorted
Yeah, cyclic
topologically.
can't be sorted.
Yeah.
मैम यहाँ पे जब अपन कर रहे थे तो 0 पहले जिसकी हो रही थी हम उसको जरूरी नहीं है पिक करें. We won't pick the one which is having inbuilt in degree 0. Like we can take any one.
Yeah, anyone with degree 0. In
But
degree
earlier
0.
there were one vertex which is having 0, but we were ignoring it, and it
Yeah,
is good.
it was 4, right? You
Yeah,
had
ma'am.
4 here, and it
And
had
I
in
thought,
degree 0.
yeah, that in degree got initially like before it got in degree 0
Because
before.
no, you don't have to decide on that basis that this got in degree 0 first, so I should be taking this one. That's not how you have to decide. You can go with any of the vertices that has degree 0 in degree 0. If these two have in degree 0 at present, then I can either choose this or this. It's up to the person who's doing the question. Okay.
Okay, ma'am.
So with this, we're done with the 10th week, I guess. I don't think there are any other topics left. So if you have to ask anything, you can.
Just a question. What is the use of topological sorting?
Topological sorting, the very first example that we gave, let's say you have you have to construct something, and for that there are activities like first thing, or there are steps. That first step, and then you have second. When I'm saying second step, I don't mean that it has to be done on the second place. I'm just numbering the steps. That's all. So if there are steps, and if I say that step 1 is required to start with step 2, or step 2 is required to start with step 3. So to decide what order should I go in, is for that reason we do topological sorting.
Okay. Okay, got it.
Anything else?
Ma'am, like what is the difference between acyclic and cyclic graph? As you have said that this one was not cyclic, but yeah, so that's my.
Let's say you have this thing V2, V3, V4, V5, and then this thing. So if the arrows are there, that means if you follow these arrows and they complete it's like in the same order. This, then next up this, then this, then this, and then this. So it's closed then. But if you will change one arrow, then it's not cyclic, right? If I'll do this thing, so you're going here, and this arrow is opposing this arrow. So in simple words, if your arrows are forming a cycle like this thing, a closed loop if they're forming, and the arrows are in this order only, so they should go in this order. That's when the loop is closed. If you have this thing and then two arrows pointing toward each other like this one, then it's not a cycle. This is not a cycle.
Ma'am, can
One
you once
question.
tell that one that the in degree, like you said, no, that in degree coming one that will be 0, and from that you decide that part. Can you just tell?
In topological sorting,
Yeah, ma'am. Yeah, ma'am. Just now, this right part, I think you wrote 4 to the 4 0, that one. How do you decide that one?
this 0, 1, you can
Yeah,
choose
ma'am.
any one within degree 0. So any vertex that has in degree 0 at the moment that you're writing things, you write that first. So if I have 4 and it's in degree 0, and let's say you have this thing 4, and then the in degree of 4 is 0, and then there is another cycle, and the in degree of 3 is 0 there, then you can start with 3 or 4, anything. So anything that
Okay.
has degree 0, you can write that here first. Doesn't matter.
In the topological sorting, right?
Yeah, the main point of topological sorting's main idea is that I should be doing the things in this order, and then I'll be okay. That means for 4, I don't require any of the previous ones. So in simple words, when you topologically sort things, this means that you don't require 1, 2, 5, 6, 8, 7 for 4. Doesn't mean that you require 4 for everything that comes after it.
Okay, ma'am, got
But
it.
everything that
Thank you.
comes before it is not required for 4.
Okay,
That's all.
ma'am.
Ma'am,
Thank you.
yeah, ma'am, in topological sorting, if we don't have any component which contains 0 degree in the beginning,
Yeah.
so how we approach that?
Then it's not a DAG. The DAG is you're saying that if you have, let's say you have a vertex V1 and none of V1, V2, V3, V4, V5, and none of the vertices has in degree 0. That means every vertex has an incoming edge, right? Then there is definitely going to be a cycle. That means that's a cyclic graph. Why?
Okay.
Because
And ma'am, if we
say
have
you have in degree here too. That means everyone has an in degree. There's an incoming edge everywhere, right?
Oh, yeah,
Either
ma'am.
it's a cycle or it could be this. This is also possible, right? You typically there's no cycle here, but we don't consider V1, V4 to be a cycle. This is not considered a cycle, but this is creating a problem, right? So when you have
Yeah.
not, yeah,
yeah, ma'am, thank you so much.
and when there are both arrows, actually it's I believe it's not required here.
Yeah, ma'am, you can
Anything
say
else?
you can
Okay,
say
okay, got it, ma'am.
ma'am, you were saying
Thank you.
something. You were saying something. If you can
No,
continue.
nothing. Nothing that's of importance. Okay. Anything else? There's nothing, we can end the session here then.
Yes, ma'am. But
Oh.
okay,
Are there
ma'am.
any other doubts or can we end the session here? Okay.
Yeah, thank you, ma'am.
Thank you, ma'am.
Thank you
Thank you,
guys.
madam.
Thank you, ma'am.
Thank you, ma'am.